So in this lecture, we're going to discuss an application of potentiometry, and you will find this in chapter 15 in your analytical textbook. And this is namely the use of ion-selective electrodes. So we'll talk briefly about sort of an introduction to what an ion-selective electrode is, and then we'll look at the setup and then do some problem solving with them. So the purpose of an ion-selective electrode is just like it sounds, to selectively determine the concentration of a single ion in solution. And in this first example, we're going to consider the potassium ion, but there are ion selective electrodes for many different ions, and in later videos we'll discuss one that selects for a proton, which is known as the pH electrode. It's always the goal to accurately determine the concentration of the ion of interest. Here the analyte is potassium, and we want to determine that concentration while minimizing the interference from other similar ions. So other alkali metals that might sort of masquerade themselves and appear as if they're a potassium ion would be ions like cesium and rubidium, both in the same +1 oxidation state as this potassium. So this ion selective electrode is different from the electrochemistry that we've been discussing thus far, in that there is no redox occurring in the solution where we're measuring an ion selectively. In other words, there's no reduction or oxidation half reactions to write. There will be a potential that we use to determine the concentration, but the potential that's measured by the electrodes in an ion selective electrode is due to concentration differences between various solutions that are in contact. That potential is not due to any redox, or in other words, is not due to electron transfer occurring. So the concentration differences will be between the filling solution, part of our ion selective electrode, and the analyte solution, which contains the unknown concentration of the analyte. So selectivity is achieved by using an ion selective electrode, which contains a selective membrane. Or in other words, these electrodes are selective because they only allow the ion of interest, in this example, potassium, to permeate into the selective membrane. And generally, This selectivity is conferred via a ligand. Ligand is often some large organic molecule, and that ligand is going to selectively bind the ion of interest. And after the ligand binds the ion of interest, and we'll symbolize that complex as ligand L bound to potassium plus, then it's going to be able to transfer it into the membrane. So if the ligand is most selective for potassium, then it will only transport potassium into the membrane instead of another atom such as sodium, etc. So after we have some selective transport of the ion of interest into the membrane, then we can determine the concentration. And the difference in potential, or the voltage, that's measured between two electrodes, one of which is the inner reference electrode, and the other electrode is the outer or external electrode. So there will be a potential difference between these, and that difference will tell us about the concentration of potassium or any ion of interest in the analyte solution. Now, of course, there must be some calibration method that is done, and the difference in potential can be related to the concentration of potassium or some specific ion if previous experiments have been done to create a calibration curve. And that calibration curve would have, for example, y-axis of voltage, x-axis of concentration or molarity. So let me show you the basic setup so you can get an idea for what it looks like. So here we have our analyte solution in blue. It's an aqueous solution in this example. In that analyte solution, you have some unknown concentration of potassium. And there are also other ions like sodium. And the role of the ion-selective electrode, which is diagrammed here, is to determine that concentration of potassium and ignore the other cations in solution. To do this, the ion-selective electrode is measuring a potential compared to the external reference electrode, which is placed directly in the analyte solution. And this external reference electrode is often a silver chloride reference, which we've talked about in previous potentiometry videos. Inside of the ion selective electrode, there's a filling solution that's indicated in gray here. And that filling solution has some fixed known concentration of potassium and other ions as well. Inside of the filling solution, so part of the ion selective electrode, is the internal reference electrode. With some fixed potential. And that reference electrode, once again, could be silver chloride reference, among others. So what is the selectivity component of this electrode is this portion at the bottom where the electrode's dipping into the aqueous analyte solution. This is the ion-selective membrane. So let me do sort of a blown up diagram of that membrane. So in this membrane, you'll have potassium, which is bound to the ligand L, and that ligand allows it to transport into the membrane selectively. And it leaves other ions, anions and cations, in the analyte solution, such as sodium. Some potassium ions are left behind as well. And you'll have other anions like X- for charge neutrality. Generally, those are hydrophobic ions in the hydrophobic membrane. And of course, there's a fixed concentration of potassium and other ions, such as X, in this filling solution as well. The concentration of the analyte potassium in this analyte solution will change depending on how many of the potassium ions are able to migrate and be transported into the ion-selective membrane. And the difference in potential, delta E, is measured in volts or millivolts. That potential will change depending on the relative concentrations of potassium in the analyte solution and in the membrane layer. From that potential difference, we can then find the unknown concentration of potassium via calibration curve. So the way that we quantify how good one of these ion selective electrodes is, or how we quantify the selectivity, is using the selectivity coefficient. And the selectivity coefficient is going to measure and express the selectivity that a membrane or an ion selective electrode has for one given ion relative to other similar ions. So for example, if the ion of interest is A, and then other ions that might interfere and masquerade themselves as if they were A, we'll consider that ion here, the interfering one, to be X. So we want to have the smallest K value possible because K measures the response to the interfering ion X, the one that we do not want to enter the membrane, and masquerade itself as ion A relative to the response that the electrode has to the ion of interest, or the analyte, A. So the higher the response to A, the smaller the selectivity coefficient will be. So we always want to minimize the selectivity coefficient. So here's an example problem where we'll do some calculations relating ion selectivity. So here, fluoride is the ion of interest, or the analyte. And hydroxide is another anion that could be similar to fluoride in solution and could bind to other cations or ligands, right? Oxygen and fluorine are about the same size, and they both have a -1 charge here. So hydroxide in aqueous solution is always potentially an interfering anion X. And this selectivity coefficient has been determined to be 0.1, which is the measure of response that this electrode has to hydroxide relative to the response that it has to fluoride, which basically means there's a 1:10 ratio where this detector, or ion-selective electrode, is 10 times more sensitive to fluoride than hydroxide. So we're told that there's a 1 × 10⁻⁴ molar solution of fluoride. And we want to know what the change in voltage would be if we have a pH of 10.5 relative to a pH of 5.5. Now, of course, a pH of 10.5 is a very basic aqueous solution. In other words, there's a high concentration of the interfering ion, hydroxide. Whereas pH 5.5 is much more acidic, and there should be a low concentration of the interfering hydroxide. So we're going to assume that in this much more acidic solution that the concentration of hydroxide is negligible. Protons are in a much greater concentration there. And the electrode here experiences no interference. So in a 10.5 pH solution, right, we can find the concentration of hydroxide that is going to be interfering with fluoride. So consider that as step 1. Of course, the pOH would be 14 minus 10.5, or the pOH is 3.5, which means the hydroxide concentration is the antilog of the pOH, 10 to the negative pOH, which is 10 to the negative 3.5, or 3.2 times 10 to the negative 4 molar. So the concentration of hydroxide is 3 times greater than the concentration of fluoride. That's why it interferes. So the equation that we'll use to find the change in voltage is derived from the Nernst equation. And this tells us that the potential due to the ion in the ion-selective electrode is equal to a constant value, and that is measured by the reference electrodes, kind of like our standard potential we've used in previous Nernst equation problems, minus 0.05916 multiplied by a log of the fluoride concentration. So first of all, at pH 5.5, when we have an acidic solution, the hydroxide concentration is negligible. And here, the measured potential should be the constant from the reference minus 0.05916 times log of the fluoride concentration, 1 times 10 to the negative 4 molar. And that gives us 236.6 millivolts. At pH 10.5, now we have a large concentration of hydroxide, and we determined that to be 3.2 times 10 to the negative 4 molar, which is no longer negligible, or this is a high concentration of anion that is interfering and masquerading itself as if it were a fluoride ion. So now the potential becomes 0.05916 times log of the fluoride concentration. So this is the true concentration here of the ion of interest, the analyte. But it appears that there is extra fluoride in solution because hydroxide is similarly charged and similar in size. However, keep in mind that the selectivity coefficient says that the detector responds to hydroxide with 1/10 the sensitivity relative to fluoride. So we take 0.1, the selectivity coefficient, and multiply it by the hydroxide concentration. So that's your K value there for selectivity of fluoride relative to hydroxide. So even though there's 3 times the concentration of hydroxide relative to fluoride, the detector only responds to that with the 1/10 selectivity. So if you add those together and take the log and then multiply by the constant, you're going to get 220s here. $229.5 millivolts. So the apparent voltage at a high pH, pH 10.5, is negative 7.1 millivolts. So the difference here, delta E, the change in voltage, is just the subtraction of the two. So it's 7.1 millivolts lower because some of the hydroxide is interfering when it's high in concentration. And this 7.1 millivolt difference would sort of tell you that you have a 32% increase in fluoride. That's what the detector says. But this, of course, is untrue. We've kept the fluoride concentration fixed at 1 times 10 to the negative 4 molar. It should have the same potential reading, or the difference in volts between the measurements at 2 different pH values should be 0 if we haven't changed the fluoride concentration. but in reality, the ion selective detector or electrode does not work perfectly. No single ion selective electrode is completely selective. But if you have large concentrations of interfering ions, then you'll get a difference in potential, and that difference in potential leads to inaccuracies, or would make one think that we actually have a 32% change in the fluoride concentration. So please be comfortable with defining these terms, relating the selectivity coefficient to the ability of these electrodes to select for one ion in the presence of other similar ions. And please be able to diagram and understand the purposes of each of the components that make up the ion selective electrode. So for more practice with electrochemistry and potentiometry, you can visit Unit 4, which is the electrochemistry unit of my analytical course guide, and that's available at chemguides.com.